So okay, it's really great to have Stefano Marseglia, one of our members here in the Institute, talking today about polarizations of Abelian varieties over finite fields via canonical liftings. So,
thank you, Albert, for the nice introduction. Thanks for coming. I think this is my first talk in person after the pandemic, so let's see if I still remember how this is done. Yeah, I'm going to talk about polarizations of Abelian varieties over finite fields via canonical liftings, and this is joint work with Jonas Bergström and Valentin Karemaka. Right, so let's start from the beginning. So I understood that this talk should be accessible also to master students and people that are not experts on Abelian varieties, so I'm going to take it easy and slow. An Abelian variety over a field K is a projective, geometrically connected group variety. The key word, I think, or at least they're all important parts of the definition, but I think the most important one is the group variety thing. So let's say a few words about what this means. So this means that we have maps, an addition and an inverse map, and a marked k-rational point on the variety that I'm going to denote by E, such that the quadruple consisting of the variety, these two maps, and the rational point is a group object in the category of projective geometrically connected varieties. So in practice, this means that we have like let's say, functorial way to attach a group structure on a variety. And with functorial, I think I want to say that you don't want to use the object of the group. You can represent it just by using diagrams. If you don't want to think about that, you can just think that we have a natural group structure on the point on the algebraic closure, on the fields in between k and k bar, but in fact you have it also on all k algebras that are nice enough. Great. And as I said, I mean, all the axioms of this group are going to be encoded using diagrams. You want something that doesn't use the objects of the group. And let me give you an example. So this is going to be the axiom of the inverse. So you start from your variety, you use the diagonal embedding into the product of the variety with itself. Then you apply the inverse on one of the two elements of the product and the identity map on the other. Then you add, and you want that this diagram, this path is the same as taking the identity element. And this is one side in inverse, and of course you want also the axiom for the other side. So you're going to do the same thing with identity and inverse swapped. And this is what is the inverse on an Abelian variety, or better on a group scheme. Okay? Cool. So when you look for examples of Abelian varieties, well, more or less, you end up like looking at Abelian varieties of dimension 1. I'm going to say more about why this happens, but Abelian varieties of dimension 1 are just elliptic curves. They are well known, well applied, they have applications everywhere in cryptography and so many things. And elliptic curves are particularly nice among all the Abelian varieties because we can always describe them with very nice and well understood equation. So if the characteristic of the field is different from 2 and 3, you can always find an equation that looks like this. So you only have two coefficients, A and B. Okay? If the characteristic is 2 or 3, you might need, I think, 3 or 4 more coefficients. And the equation is still like very explicit, just a bit longer. And using this model of the elliptic curve, you have that the rational point that is the unique element of the group scheme is going to be the point at infinity, the unique point at infinity. Cool. And the group law also for elliptic curves using this model can be described very, very explicitly. So if you take a point, then the inverse of this point is going to be just the same point with a fine y coordinate with a sign minus in front of it. So same x and you put a minus in front of the y. And if you want to add 2 points, more precisely a point and that is another point that is not its inverse, then you can use these formulas. Okay? So these formulas, I mean, I'm representing them as a fraction, but of course I'm just taking the inverse in the field that we are working in. So they are not important for our talk, but I just want to convey that the formulas are explicit and they're really like hands-on. You can really like do whatever you want. You can do computations using these formulas. Okay. Over the real numbers, elliptic curves can also be, you can also provide a graph of this elliptic curve. And they look something like this. So this is the example of the elliptic curve y squared equal to x cubed minus x plus 1. And if you draw the graph, you get this red line, this red curve. As you can see, it's symmetric with respect to the x. And this is useful when you want to describe the addition law explicitly. So you take 2 points on the curve. By Bézier theorem, you're going to have like a third intersection when you count in multiplicity. So if the 2 points coincide, you're taking the tangent line. So you still get a third intersection. and then you reflect this third intersection with respect to the x-axis, and this is going to be the addition of the 2 points. Okay? So, great. All right, now let me, so we're going to talk about polarizations of abelian varieties. So we're going to make like a little jump now. So we're going to abandon dimension 1, we're going to work with a general abelian variety of any dimension. And let me first introduce some very important concepts that come with abelian varieties. So the first one is the notion of isogeny. So an isogeny is a particular kind of homomorphisms between 2 abelian varieties. So map between 2 abelian varieties. So homomorphism, this means that it has to be a morphism of variety that is compatible with a group law. So it's a group scheme homomorphism, right? And map is an isogeny if the 2 varieties have the same dimension and it is surjective. Or equivalently, if it is surjective and it has finite kernel, finite as a group scheme. And indeed, that's what I wrote here. And the degree of the isogeny is defined as the rank of this group scheme. Okay? So you can think of isogenies as a generalization of isomorphisms, maybe, because they are surjective and the kernel is not necessarily trivial, but it's finite. So that's what happens. Great. So another important thing that you can do with an abelian variety is to form the dual variety. The formal definition is the following. So you take the Picard functor associated to the abelian variety, to the connected component of the neutral element. This functor is representable by another abelian variety. Very fancy definition, but that's not going to be very important in what follows afterwards. The point is that there exists an abelian variety, which is the dual, and I'm going to tell you later how this behaves. Among the isogenies between an abelian variety and its dual, some are special, and they are called polarizations. So the formal definition is the one here on the screen. So polarization is an isogeny between an abelian variety and its dual, such that when you possibly after an extension of the space field, this isogeny comes from an ample line bundle. So this means that on points looks like this. So it's like a translation of the line bundle times with the inverse of the line bundle. In practice, at least the way I think about polarizations is that since they come from an ample line bundle, they sort of contain some data about how this abelian variety is projected. So how they remember some information about how they are embedded inside the projected space. So if you've seen ample line bundles, you know that an ample line bundle to some power becomes very ample, and very ample line bundles are the same as projective embedding. So make it a long story short, but that's what this polarization sort of records. Why? Just like a terminology, if a polarization is actually an isomorphism, so if it has degree 1, then it's called principal. Okay, and principal polarizations play an even more important role. And let me tell you something about that. So why do we care about these polarizations? All right, so the first reason, actually the reason 0 that is not on the slide is that, I told you that the typical example of an abelian variety is abelian varieties of dimension 1, which are elliptic curves. Turns out that elliptic curves are always self-dual, so they're isomorphic to their own dual, and they admit a unique principal polarization, which is canonical, so they're constructed canonically. So one could argue that the right generalization to higher dimension of an elliptic curve was not really a general abelian variety, but it's a principally polarized abelian variety. So that's maybe like a meta reason why they are important. But at least 2 of the most important reasons that I found are the following. And the first one is that when you look at the automorphism group of an abelian variety, so the isomorphisms for the abelian variety itself, if you just look at the abelian variety by itself, this group is typically going to be infinite whenever the dimension is bigger than 1. And if you want to formulate like a moduli problem and construct a moduli space, you want to really stay away from infinite automorphism groups. Adding the polarization to the datum, so taking an abelian variety together with a polarization, adds rigidity to this problem. And in fact, you get that the automorphism group is finite, and you can formulate much better moduli problems. So this is one reason why do we care about polarizations. And the second one is that this is useful to study curves. So if you take a proper smooth curve over your field, then you can construct an abelian variety out of it, which is called the Jacobian variety. And it turns out that this Jacobian variety admits a principal polarization. You can canonically construct from the curve a principal polarization attached to this Jacobian. So in other words, what I'm saying is that studying the abelian variety together with the principal polarizations allows you to get information from the curves. And also on the moduli space attached to curves and abelian varieties, if you want to think in those terms. Because this construction allows you to construct a map from the moduli space of curves to the moduli space of abelian varieties. Indeed, for every curve of genus G, you will get a Jacobian of dimension G. And this map, well, it's still like, some parts of it are like well understood, others are still pretty mysterious. So for example, we know that is surjective. Let me put it between quotes because we have to consider also products in order to make it surjective. But it's surjective if you work with dimension 1, 2, and 3, essentially. So every principally polarized abelian variety is going to be more or less like a product of Jacobians for these small dimensions, but we know that this is not true in higher dimension. So this means that, yeah, we don't know, and we don't really know much about the image of this map. So this is also like something that we would like to study, and why do we care about principal polarizations. All right, let's move on. So this talk is going to be about finite fields, but actually complex abelian varieties are going to play a very important role. And this is nice because, as I'm going to show you in this slide, complex abelian varieties are much nicer. They are easier to describe. Well, C is the nicest field that you can do geometry on, I think, right? So let's take A to be a complex abelian varieties, let's say of dimension G. It turns out that when you look at the complex points of this variety, you can always describe them as a torus. So G-dimensional vector space modulo a lattice. So this lattice is just a free abelian group of rank twice the dimension. Okay, so yeah, after you choose like a basis in an appropriate way. So this is a torus, right? The torus are much nicer to understand than the fancy object we talked about before. But it's not true that every torus comes from an abelian variety. You need like an extra piece of data. So indeed, if your torus is an abelian variety, then admits a non-degenerate Riemann form, which is just a matrix representation of your polarization. So your polarization is going to use this antisymmetric and positive definite Riemann form. So you can think of it really as a matrix. This is going to act on your lattice. So it's a real matrix, nothing too complicated there. And in fact, we have an equivalence between the categories of abelian varieties over the complex numbers and the tori admitting such a Riemann form. Okay, good. So you can pretty much get all the informations that you can describe using maps using this tori together with the Riemann form. This is what an equivalence of category is, right? So it's really a nice tool. On the other hand, we know that when we leave characteristic 0 or the complex numbers, this equivalence cannot work. And let me say something about it. So already in dimension 1, there is an abstraction to the existence of such an equivalence. So there are some elliptic curves, so abelian varieties of dimension 1, which are called supersingular. So an elliptic curve is supersingular if the p torsion has rank 0. So you take the group of points of your elliptic curve, you look at the p torsion of it, and if it is a 0, then the elliptic curve is called supersingular. Okay? And it turns out that some of the supersingular elliptic curves, also if you look at them over the algebraic closure, they are going to have a quaternionic endomorphism algebra. So endomorphism algebra is just the maps from the elliptic curve to itself. Okay? And you tensor it with Q because you want to turn this ring into an algebra, but we're not doing anything fancy there. And they are quaternions. So if such an equivalence existed also in characteristic P, then you take the lattice associated to the supersingular elliptic curve, the endomorphisms are going to be the map from the lattice to the lattice, then you tensor with Q because we are looking at the algebra, and this means that you would have constructed a representation of a quaternion algebra of dimension 2 over Q, and this thing cannot exist. So this means that such an equivalence cannot exist in full generality over the whole category of abelian varieties in positive characteristic. Okay, so this is an abstraction. All right. So we're going to have to be more careful when we work over finite fields. Great. Any questions so far?
Yeah, sure.
Yeah.
So when you say this equivalence for characteristic P, you say this custom sort of lattice, are you thinking of like FP, like FP bar, then mod up by some lattice?
No, this would be still okay.
C, or
I'm sort of like pretending that this c to the power g is not there, so that you look only at the lattice. Because in fact, I mean, here all the arithmetic information is not really in c to the power g, right? Because that's right. So the only information is considered. So you could describe it as a vector space of dimension g, and then a lattice inside it. But then you change the basis and you say, okay, the vector space upstairs doesn't really contain the information. You just look at the lattice.
Okay.
So in fact, information is only contained in the lattice. It's just that describing it as a torus is more geometrically. You see like that it's a torus, right? So you want to not just remember the lattice. But yeah, good question. So interrupt me any moment if you have any questions. All right. Great. So, yeah, okay, I wanted to actually add something here. So, this equivalence, this is more a fun fact, it's not really related to the talk, but if you look at this equivalence, it's actually very nice also because it allows you to represent abelian varieties in a very compact way, right? You just need to remember this lattice, and this is rank 2G, so it's, what, 2G complex number, 2G vectors in C, so it's fairly compact if you think about it. It's a bunch of complex numbers, but it's still like a few of them. And why this is interesting? Because, so, when you start reading about, or at least that's what happened to me, when I start reading about abelian varieties, I was like, okay, let's look for some examples. Then you see elliptic curves, product of elliptic curves, and you're like, okay, is there any concrete example of dimension higher than 1 that you can find? Well, it turns out that you don't want to write down an example of dimension higher than 1, because it was proven that already in dimension 2 you will need 16 variables and 72 equations to describe the general surface. So this is in the book by Flynn and Castles on the, it's a funny title, the proglomena of a middle brow of a curve of genus 2. And they proved, they made a calculation that if you want to use equations, they exist because the varieties are projective, right? That's almost by definition we do have projective equations, but you really don't want to use them because you need so many, and if you don't even start thinking about like how the group law is going to look like using all these equations. So using lattices is great. So that's what I'm trying to sell here. Like this is a great way also to write down what an abelian variety is. All right, but let's move on now. So one of the techniques that we're going to use in one of the key techniques is this notion of canonical liftings. So I told you in the previous slide that complex abelian varieties are nice, and in positive characteristic they are wider, they are harder to understand. Nevertheless, sometimes we can do the magic. We can start from something in positive characteristic and go upstairs to characteristic 0, and then you just take extend the coefficients to C, and you are in a complex world. So let me say about this technique and how it works. So we start with an abelian variety of dimension G over a finite field of Q. Q is a power of prime P. I'm going to denote these abelian varieties by A naught with the naught. And a canonical lifting, so it's an abelian scheme defined over a normal local domain, which I'm going to denote by R, which has characteristic 0, this is crucial, and a residue field of Q, such that the special fiber, so the reduction, is the abelian varieties that you started with, the one over the finite field. And the second property is that the general fiber, so when you look at a fraction field of this domain, so a field, is an abelian variety such that all the endomorphisms are still there. So let me comment about this. This second property is very special. So let me say why. So when you have like an abelian variety, or in general varieties over positive characteristics, they are naturally endowed with more morphisms. There are more maps there. Why? Because when you look at a ring in positive characteristic, let's say a finite field or whatever, you have like the maps like the Frobenius one, that you take an element, you raise it to the Q power or to the P power, and this is a ring homomorphism. Because when you expand, it's additive, right? When you take x plus y to the power P, there are going to be a bunch of binomial coefficients in the middle, they're all divisible by P, so they all disappear. So it's additive. This is really a property of characteristic P. These maps cannot exist in characteristic 0. So this is a ring homomorphism on the coordinate rings of your abelian variety, so it induces a map also on the geometric objects. So these maps come with a Frobenius endomorphism, something that acts like that. And this is a map that is intrinsic, as I said, belongs to positive characteristics to the finite fields, and it cannot exist in characteristic 0. This map is not a geometric map. And so this condition too that's why it's very special. So we are saying that all the map, including this Frobenius, exist up there. So of course I'm not saying that there is a Frobenius there, but there is a map that reduces to the Frobenius. Okay? So it's a map that after you reduce to FQ, so you something leaving characteristic 0, you reduce and you get your original Frobenius. So this is quite a strong condition. It's not empty at all. I mean, it's really like an important one. All right. So how often does it happen that an abelian variety admits such a canonical lifting? Well, even if this is very special, it turns out that most abelian variety, for precise meaning of most, admit a canonical lifting. So among all the abelian varieties that are the one that are called ordinary. So ordinary is somehow at the other side of the spectrum of supersingular. So supersingular, I told you, that is trivial p torsion, and ordinary is maximal p torsion. And as the name suggests, that's the general case. This can be made precise when you look at the moduli space. This is the biggest stratum in the moduli space of the abelian varieties, but in practice you should think that most abelian varieties are going to be ordinary. So they do admit a canonical lifting, and also the one that are almost ordinary, which is the rank of the p torsion is 1 minus the maximum. So the maximum is achieved by the dimension, so you can always have to the power g, and this one is g minus 1. And in fact, the almost ordinary ones, sometimes they have a unique canonical lifting, sometimes they have two. Fun fact. But it's not true also, is not every abelian variety admits a canonical lifting, and we kind of already have seen this counterexample, this object that makes the whole nice things break down. So supersingular elliptic curves, they do not admit a canonical lifting. And the reason, as you can see it, is that, as I told you already before, they have like a quaternionic endomorphism algebra, and there is a classification of which endomorphism algebras can occur, and it turns out that in characteristic 0 you cannot have quaternions in dimension 1. So all the elliptic curves in characteristic 0 are going to have an endomorphism algebra which is either Q or quadratic number field. So it's commutative in particular, so you cannot get quaternions then. All right. Yeah. So canonical lifting are going to be very important. So it's good that we discuss them. And yeah.
You said almost ordinary abelian variety. That means.
P rank g minus 1.
So then the elliptic curves that are almost ordinary.
Yeah, that's the okay. I should stay away from quaternions. Okay. Fair enough. Yeah, that's exceptional. Yeah.
Okay.
I've seen somewhere it's people defining like almost ordinary only for dimension bigger than 2.
Yeah.
I don't know if it's cheating or, but yeah, the one should stay away from these kind of things.
And canonical lifting is what you define here, but
yeah, that's
but they are not canonical in the sense that there is only one, because you also
no, exactly, no. Maybe the word canonical. We didn't choose this word. It's something in the literature. So, but yeah, canonical refers to this second part. So a lifting is something that reduces to what you started with, and canonical means that it's well. In this case, I guess you should interpret canonical as the nicest, the one that behaves better than all the others. Okay. So the next important tool is what is called complex uniformization. This is a technique that allows you to associate, in a precise sense, to an abelian variety characteristic 0, like a torus or better the lattice. We already seen it in the previous slide, but we're going to discuss in more detail what's actually going on in the context of canonical liftings. So let's assume that A0, A0 is our abelian variety over the finite field that admits a canonical lifting. Okay, so we assume that. And so R was the normal domain, normal local domain where the canonical lifting was defined. And we can embed it inside a complex number. So typically this is going to be some local ring, some extension of the p-adic numbers. But there is this, let's say, magical isomorphism between QP bar and C. It's a funny isomorphism because I think its existence is proved using Axiomov's choice and some weird techniques, but there exists such a thing. So the point is that you can embed R inside the complex numbers. And then you can extend the coefficients of your canonical lifting and you get like a complex abelian variety. All right. As I said already before, all the endomorphisms lift, and in particular we get something that reduces to the Frobenius, to this Q power map. And well, to be precise, there is also another map that is important, which is the Verschiebung, which is just Q over the Frobenius. But I think the Frobenius is the key, the core of the story, and then the other one tags along. So complex uniformization is like an extended theory that tells you that you can, in this context, in this situation, you get a torus. So this is going to be the torus that we're going to land in. But the torus can be described in a more precise way than what I said before. Before I said it was a lattice, but here we actually know a lot more of this lattice. We can see more structure. And in particular, you can describe this torus, so the lattice, as the image of some fractional ideal. So let me say a few words about these things. So you consider the ring generated by this Frobenius and this Verschiebung. Okay, so Z linear combinations of powers of F, and this is a subring of the algebra generated over Q generated by the Frobenius. And inside this you take an ideal, and the ideal should have like maximal rank as a Z module, but let's not worry too much about that. It's a fractional ideal. Fractional just means that you might have denominators, but after clearing denominators you get an honest ideal of your ring. Phi is a CM type. So a CM type is a choice of half of the maps from your L to the complex numbers, and you pick one per conjugate pair. Okay, there is a lot of information, but this algebra comes with an involution, the one that changes the role of F and B. And this involution is going to act as complex conjugation after you apply any map to C. Okay, if you think a little bit, this is, yeah, you can prove it. It's quite easy to prove that F and B are the complex conjugate after you apply any map. So for every choice of maps, they come in pairs, and you pick one per conjugate pair, and you take G of them.
May I ask?
Yeah.
So when you buy this F and B and you call them varieties and Verschiebung, that just names.
Yeah.
When you describe as a polynomial and you two variables which satisfy the relation that F times B is Q.
Yeah. So, and I'm going to say more about the polynomials that they to satisfy in a second. But yes, they are just algebraic numbers, let's say, or integral.
Variables. Variables. It's polynomial rings.
You can think of them as roots of a polynomial with integer coefficients, but I'm going to get there in a second more precisely. Yeah. So, right, so this torus is described in this way. So you have like phi of a fractional ideal. Right. And I'm going to just introduce the notation for the next couple of slides. I'm going to denote this ideal as H of the canonical lifting of A. Right. So we have this association. And the reason why I want to introduce this notation is that I want to repeat the whole story for the dual of your Abelian variety. So you start with the dual of your Abelian variety over characteristic 0. You get a canonical lifting. Turns out that the construction of the canonical liftings is compatible with taking duals, so you add one. We again extend the base field to the complex number in the same way as we did here. We get a canonical lifting over C of your original Abelian variety, and then you apply this. You look at the torus and you look at the fractional ideal. Turns out that we understand this fractional ideal very well once that you know I. Indeed, the ideal is just going to be the trace dual ideal with a bar on top. So trace dual is just the set of elements inside your ring, inside L, such that the trace of x times I is integer valued, and then you put a bar on top. So the definition is not so important for us, but it's concrete, it's very hands-on. Once that you know what the ideal is, it's very easy to construct what this other ideal is. So in this sense, what I want to say is that the dual over the complex number is also well understood. So we had this fancy definition, and here is just like another ideal, which is a trace dual ideal. All right, cool. And in particular, so we are interested into polarizations. And as I told you before, polarizations were mapped from the Abelian variety to the dual. So this the homomorphisms between the Abelian variety and the dual using this description in terms of fractional ideal is also fractional ideal. It's the colon ideal I bar t colon I. This is just the set of elements of the ring that sends your fractional ideal I inside of the dual. So they are the maps from the ideal to the dual, and this is what we are looking at, the maps from the variety to the dual. Alright, so we have this, the point of this slide is that we have a description for the canonical lifting of the home set using fractional ideals. Great. So here I'm just repeating the notation that I put in the previous slide, just for convenience. So torus, torus, home set in terms of colon ideal. The polarizations. So as I claimed before, the polarizations were these Riemann forms, these matrices satisfying symmetry and positive definite. Let's see what this means in terms of this element of these rings in this fractional ideal. It's even more concrete now. So you take an homomorphism from the variety to the canonical lifting to the dual, and this is, let's say that is an isogeny. Then it is a polarization if and only if the corresponding element in the colon ideal satisfies the following two properties. So one is totally imaginary, so lambda equal to minus lambda bar. Okay? So this is a very algebraic condition, it's only happening in a ring. And the second one is that it's phi positive. So phi positive means that you take the image of this element with respect to any homomorphism inside a CM type, and then you take the imaginary part and you want it to be positive, strictly positive. So I think a good way to think about this CM type is that it tells you what is the complex structure on your torus. So a complex structure basically says, so if you think of C over as an extension of the real numbers, you can look at it algebraically as generated by x squared plus 1, right? And then you want to say, okay, one of the two roots is going to be I, so it's the one that stays on the upper part of the top half plane, and the other one is going to be the one in the imaginary part. So you want to say what is positive, what is negative. And this is what we are reading here. So CM types allows you to tell you what is positive and what is negative. And polarizations are precisely the one that are going to be phi positive. It's just that it's more embedding, so you don't have only, it's not like C over R, you have, well, two embeddings, here you have like a bunch. But the idea is the same. Okay. Right, so we understood the canonical liftings. Are there any questions on the previous slides?
Yeah. So A can check. That's the
dual?
Is it the canonical lifting of the A not check?
Yes.
Is the other way around?
It commutes. So the two constructions are compatible with each other. So.
And so A naught is some Abelian variety over finite field.
Yeah. The canonical lifting, well, the formal definition was over this local domain, but then we extended to the complex numbers. So, and you don't lose any information in using the extension.
When you define this like canonical lifting, I thought you said, can you go back to that page? I thought it said some, I have lots of words.
Yeah.
It says A naught is an Abelian scheme over a normal local domain.
Yeah.
But you're now saying A0 is a Abelian variety over F cubed. Is that what that means?
So A naught is the special fiber of this scheme, which I didn't put a letter.
Okay,
so it's the reduction.
Yeah.
Okay. And then in this scheme, actually we don't really want to work on the scheme over R, but you want to work with a general fiber. So it's the over the, because you want to work with a variety. But the appropriate way to do it is, so you don't have a reduction map from Q to FP. You have a reduction map from Z to FP, right? So that's why you have to do these intermediate steps with Abelian schemes. But, yeah.
So when you go back to where you were, the next slide for the ICM type, I would like to see this definition.
So G is the dimension, maybe it's not.
So ICM type is just a map.
Is G maps. So L admits two G maps to the complex numbers. That's it's not because F is going to be a root of a polynomial of degree 2G. And so you have two G maps to the complex numbers, one for each of the roots, and then they come in conjugate pairs, and you take one per conjugate pair, so G of them, half of them.
Okay, so does this mean that you are choosing the roots of the characteristic polynomial for these?
That's the next slide. Right. So over FQ, now let's stop talking about canonical lifting for a second, and we talk about the classification over FQ. Over FQ, I already told you that your abelian varieties come with this Frobenius map. We have Frobenius, and in fact, to the Frobenius, you can associate a matrix in the following way. So you construct first the LI dictate module. So you pick a prime different from the characteristic. You take the L power torsions points of these abelian varieties over the algebraic closure, and you put them in an inverse limit. Okay. Turns out, well, there's a theorem of, I think, data, or I don't know, that this object, this module here, is a free CL module of rank twice the dimension. Okay, so your Frobenius map, this construction is punctorial. So you get, from your Frobenius, you get an induced Frobenius on the LI dictate module. After choosing a basis like we're doing here, you can represent it by a matrix. And you can take the characteristic polynomial of this matrix. In fact, so this construction, the characteristic polynomial you get is what is called a Q-Veil polynomial, which is a short form for many important things. One of them, for example, is that this construction doesn't depend on the choice of the prime L, as long as it's different from P. And indeed, this polynomial is integer coefficients. Another thing that you can say is that this is a polynomial of degree 2g, right? Because it was a determinant of a matrix 2g times 2g. The coefficients are going to satisfy certain symmetry. And another important thing is that the roots, the complex roots of this polynomial, they all lie on the circle of radius square root of cube. Okay. Another very important thing is that they're an isogeny invariant. So if you take two abelian varieties that are isogenous, then they're going to have the same characteristic polynomial of the Frobenius. And also there is finitely many once you fix the dimension, because, well, the roots are all on the circle, so the coefficients are symmetric polynomials in the roots. You can bound these coefficients in some very naive way. Yeah, there is finitely many, right? Because they have to be integers, as I told you. Great, and in fact, so here we have we can construct a map from the isogeny classes of A to the characteristic polynomial, because this is an isogeny invariant. And I told you that this association is injective, and in fact, Hong and Tate proved that it's also almost surjective. So there is an almost, because it's not true that for every Q-Veil polynomial, so a polynomial satisfying this condition that I just told you, there exists an isogeny class, but almost. So when you look at a factorization into a reducible of this polynomial, sometimes you have to take some powers, and this will give you like an isogeny class. So these exponents that you have to put are explicitly, we understand them, there are formulas to compute them. So you can think of this as a bijection in practice. So we understand the isogeny classes in terms of this characteristic polynomial. And in fact, there are some very efficient algorithms to make a list of them. And the best way to get them is to go to the LMFDB, this L function modular form database, and just click download, and you get like a bunch of them. And that's how I do it usually, to generate them. Okay, and they represent the isogeny classes. So the content of this slide is that we do understand abelian varieties up to isogeny, because every isogeny class is uniquely determined by a polynomial for which we know a lot about. Great. Non-important hypothesis that I'm going to use later is that I'm going to work with abelian varieties whose endomorphism ring is commutative, and this, again proved by Tate, turns out to be equivalent to have this characteristic polynomial square free. So irreducible, no repeated irreducible factors, or no multiple roots if you prefer. Okay, so this is something that we are going to use later on. Okay. And this maybe answer your question from before, that like about the CN type. So the algebra generated by F is just Qx divided by this polynomial. And this is a polynomial of degree 2g. We have 2g complex roots, and I'm embedding into some homomorphism to C is just a choice of this root. So, and they come in conjugate pairs. Great. Now we want to refine this. So this is a classification up to isogeny. What can we say about isomorphism classes of the abelian varieties? Well, sometimes we can do some nice things, and in this case I'm going to restrict myself to prime fields. So fields with a prime number of elements, only FP, not FQ. Okay, There is this big theorem by Centelleghi and Stix. So this is actually the 2015 theorem by Centelleghi and Stix. There's also a new version from December maybe, but we're going to work with a simpler one, which works over Fp. And this tells you that if you take an isogeny class defined over a prime field, whose characteristic polynomial is square-free, so this hypothesis that I told you I want to work with, then you take L to be the algebra generated by the Frobenius, which is just Qx divided by the polynomial. V is going to be the Verschiebung again, so it's just P divided by F, this is the notation. Then we have an equivalence of categories between the abelian varieties in this isogeny class and the category of fractional ZFV ideals inside the ring. So the maps here are just ZFV linear maps, so maps as of modules. Okay? And let me say something about the functor. So the key point of their proof is that in such an isogeny class, there exists an abelian variety with the smallest possible endomorphism ring, which is just the ring generated by Frobenius and Verschiebung. So the endomorphism rings of the abelian varieties in this isogeny class are going to be between the ZFV and the integral closure of the integers of Z inside this algebra L. And in fact, they will all occur. All the rings, intermediate rings, will occur. But the important thing is that there exists an abelian variety with an endomorphism ring ZFV, the smallest possible one. And the functor that induces this equivalence is just the homomorphisms of abelian varieties from whatever you're looking at to this particular abelian varieties, this minimal abelian variety. This abelian variety sometimes is not unique. It's not necessarily unique even up to isomorphism. There is a Picard group action of this ring on the set of isomorphism classes of these abelian varieties. And in our paper, we exploited this freedom to choose these abelian varieties in order to force duality to play well with what we want to happen. So the dual of any abelian variety in the isogeny class is going to be represented by this equivalence of categories by the trace dual ideal with a bar on top. So the same object that we had using complex uniformization in the complex world, right? So maybe you already see where we are going. We want to compare what we have in the complex worlds with these things that are happening over finite fields. But here requires more work in order to get there. Yeah, so but now, exploiting this choice, we can take this functor to be compatible with duality, and also duality for the maps. So it turns out that the dual of a morphism is just going to be the element representing the morphism with a bar on top for any isogeny for any map in this isogeny category. Great. And in particular, this is maybe the key point, is that the homomorphisms between any abelian variety in the isogeny class and its dual are going to be represented again by a colon ideal. So these ideals are going to be the images of this functor, right? So a colon ideal there as well. All right. So we have two descriptions using colon ideals. Let's compare them. So again, we're going to use all the assumptions that we had before. So we assume that in the isogeny class there is one abelian variety that admits a canonical lifting. And I'm going to denote it by A0. Now we have two descriptions using the fractional ideals, which are the following. So you take your abelian variety over Fp. You have the canonical lifting, that is the reduction map that goes down. And then we have the complex uniformization construction that I told you before. And you get this colon ideal. Okay, cool. Now, from here we can also apply the Centelleghi and Stix factor, the one that was working over Fp. Okay, and we get another colon ideal. And in fact, we prove that these two colon ideals are the same. So it's maybe if you're looking carefully, you notice that the trace dual, so the ideal that represents the dual is in the opposite place, here and here. And the reason is that the Centelleghi and Stix factor is contravariant, while complex uniformization is covariant. So it's quite non-trivial that we have an equality here, that the home set are represented by the same colon ideal, even if the colon ideal is constructed sort of in the other way around. All right. But the problem that I'm going to discuss later if I have time is that the reduction map here is not trivial. It's gonna so in the language of fractional ideal is going to appear here, and we're going to represent it as multiplication by an element alpha. And we prove that this alpha is totally real, so it's equal to its own bar. And it's a unit in the endomorphism ring, so it's an automorphism of you can think of it as an automorphism of this abelian variety, the one that we lift. So it's a unit there. Okay? Now we want to look at the rest of the isogeny class. So we take any other abelian variety in the isogeny class and we pick an isogeny from the one that we can lift. So they are isogenous by definition, so there exists such an isogeny. Now we get the induced map on the home set. It's just going to be F composed with whatever, composed with a dual. I'm going to call it the F star. And then we apply the functor and we get a GF star here. So fractional ideal, same as the one before, and we have a GF star. So one, it's not hard to prove using the definitions of polarizations that F star, so something that looks like this, so F and its dual is going to send polarizations of B to polarizations of A. And it turns out also, if you look at the definition, that this GF star is going to look like this. It's going to be a GF, some elements times its bar. So here I'm using that the endomorphism algebra is commutative because you see that the composition becomes just a product. So what is in the middle sort of like doesn't really play a role there. Okay? And this element is totally positive. So it's something times its bar. So it's totally real but also totally positive. Whenever you send it to C, you're going to get a positive real number. Okay? And why is this important? This is important because it sends total imaginary elements to total imaginary elements because it's totally real, but also 5 positive elements to 5 positive elements. It doesn't mess up with positivity because it's a totally real, totally positive real number. It's a positive real number. Okay, cool. And so this is the same diagram that I had in previous slides. We want to understand the polarizations for this random abelian variety in the isogeny class, B0, and we do understand the polarization of the canonical lifting using complex uniformization, right? So we chase the diagram. We take an element mu in here. We go, well, you choose which way you want to go, and you get this element alpha inverse, GF star, G of mu. So I'm just multiplying here and then taking alpha inverse here, right? Or if you prefer, go the other way around. And the theorem that we proved is what I call here lift and spread. So you get that mu is a polarization if and only if the element here, without the G of F star, is totally imaginary and phi positive. So the same conditions that we had in the complex world for the canonical lifting. So yeah, we understand the polarizations of the canonical lifting in terms of these total imaginary and phi positive elements, and then we can put it back this information for any abelian variety in the isogeny class. And the G of F star disappears by what I said before. It's a totally positive element. So it doesn't mess up any of these two conditions. So you can just cancel it from the equation. Okay? Good. So using this theorem, we can understand the polarizations of any abelian variety. And let me say a few words about how do we compute them. So the goal is to pick an abelian variety using this Gentile-Eigen-Stix equivalence, represented using this Gentile-Eigen-Stix equivalence. We want to make a list of all the principal polarizations of this abelian variety up to principal polarized isomorphism. Right? So all the ones that are genuinely different. So some notation just to, because we need it. So the endomorphism ring of this abelian variety P0 in the isogeny class is going to be denoted by T, and J is going to be the idea representing it. We assume that it's isomorphic to the dual, so we are interested in principal polarizations here. So if there is no isomorphism between the abelian variety and its dual, of course, there's not going to be any principal polarizations because principal polarizations are isomorphisms. So we pick an isomorphism, and this is going to be represented in the equivalence of categories by multiplication by an element. So an element that sends an ideal inside its dual. I'm going to denote this element I naught. And it turns out, if you chase some diagrams, that two principal polarizations of B0 are going to be isomorphic. It's going to be induced like isomorphic principally polarized abelian varieties. If and only if there is a unit, an automorphism of the abelian varieties, so some elements in T star, such that V bar sends one polarization into the other. So this is just the definition of an isomorphism of polarized abelian varieties uses the Gentile-Eigen-Stix language. So units, so you have an automorphism, you have its dual, and this is one is going to be V, the other one is going to be V bar. And everything is commutative, so you can just look at them as multiplication of elements. Cool. And I'm going to denote this finite quotient, so the automorphisms modulo, the automorphisms of this form by this fancy T. And we actually, the fancy T, I want to take one representative of this finite quotient. And then the set of principal polarizations of your abelian variety B consists of this set of elements here that I'm going to denote by this P, alpha, and phi. So you take the isomorphism, you apply some automorphism, and then you want to check if it satisfies the criterion that I put in the previous theorem for being a polarization. So alpha inverse times the element has to be totally imaginary and phi positive. So this is a finite set because it's indexed by, this is actually a subset of the elements indexed by T, and T, as I said, is finite. Cool. The problem is that it depends on this alpha, and we don't really know everything about this alpha. We know it's a totally real unit, but might very well be non-totally positive. So that's actually an issue. And yeah, let's put it on the slide once more. So it depends on alpha, and this is one of the two issues that we are going to address in the rest of the talk. So one is that we don't know everything about alpha, and in order to compute this set, we need to understand something about it. And the second one is the one that I just sort of like swiped under the carpet so far, is that we always assume that there exists a canonical lifting in the isogeny class. How often does it happen? So I'm going to answer these two questions. How to deal with alpha and canonical lifting.
Sorry.
No.
So do you also somehow have to make sure this polynomial or something is square free?
Yeah, but that you pick. So
okay.
my input is the characteristic polynomial, and my algorithm only works for square free. So yeah, and what is in this talk is only about square free. So that's your input. So you choose it to be square free. Okay. So first I'm going to address the problem of alpha, and I want to give at least one of the two theorems, because I don't think I have time to talk about both, but let's talk at least about one. When can we pretend that alpha is equal to 1? So that's what I mean with ignore alpha. All right. So the theorem goes as follows. So I'm going to denote by T the endomorphism ring of this generic abelian variety in the isogeny class, the one that we want to compute the principal polarization of. And S is going to be the abelian variety S is going to be the endomorphism ring of the abelian varieties that we know we can lift. So we are still assuming that there is one. Now we look at the totally real units of these two rings. Okay? And if we have this inclusion, so the ring of endomorphism of the one that we can lift has totally real units that is inside the group of totally real units of the endomorphism ring of what we are interested in, then the set of principal polarizations that we had in the previous slides, which depends on alpha, is in bijection with the same set where we put alpha equal to 1. So basically you make it disappear from this condition. And this is the second set. Okay? So if you have this inclusion, you can ignore alpha. And the proof was basically in the previous slide. So when you compute the principal polarizations, you have to look over the representatives of this here, of this quotient here. And alpha was a totally real unit. So it's something that lives in between this quotient. So the contribution of alpha is going to be taken into account when you look at the whole set. So it doesn't play a role if we have this inclusion. Because if the ring alpha is a unit, is an element inside here. If this ring is bigger than T, then we are not going to take it. It might mess up the computation. But if we have an inclusion, then it's going to be taken into account just by looking at the whole list. Okay, corollary. If we can lift something with the smallest possible endomorphism ring, which is CFV, then we can ignore alpha always. And this happens, this is something that I'm just telling you, this happens in the ordinary and almost ordinary case. Because in that case, every abelian variety needs a canonical lifting, so we can particularly lift the one with the smallest possible endomorphism ring. So with this inclusion, we'll always be satisfied. So with our machinery, we recover the results that were already known and proved by Delin and Hall for the almost ordinary, the ordinary case, and Oswald and Shankar in the almost ordinary. Right. I think I'm short of time, so I'm gonna maybe skip Theorem 2. No, let's say a few words about this. So this Theorem 2 again allows us to ignore alpha, but using a different approach. So we shift the problem a little bit. So we don't look at one particular abelian varieties, but we choose one endomorphism ring, and we look at all the abelian varieties with that endomorphism ring. So don't look at the slides because it's full of notation. Listen to me. So you look at all the abelian varieties with that endomorphism ring, and then we do the following. You pretend that alpha is equal to 1, so ignore alpha. And you compute the polarizations, but not just for one CM type, the one that was coming from the canonical lifting, but you do it for all the CM types. So there is 2 to the power g CM types, so this is a finite thing. If you always get the sum of the elements, so the number of the principal polarization is always the same, then you know that this is the right answer. This is the content of this theorem. If the output is always the same for all the possible things, then you know that this is the correct one. And the reason is that, yeah, you can see it in this proof, but again, maybe it's better if you don't look at the slides and you just try to listen to me, is that this alpha is a totally real element. The totally real units, the totally real elements act on the set of CM types, right? Because CM type was determining what is positive and what is negative. A totally real element might switch this role, but still it doesn't mess up like what's going on. So it tells you like, okay, something that is positive might become negative depending on the sign of this totally real element. So in other words, it sends the output that is coming from the correct CM type, the one from the canonical lifting, to the output of some other CM type. We don't know what alpha is, so we don't have a control of what is this other CM type. But if all the outputs for all the CM types are the same, which was the content, the assumption of this theorem, so if the output is always this number n, you always get the same number, then it must be the correct one. And as a consequence, you also get that even if the outputs are different, you know that one of the possibilities is going to be the correct one, because this is precisely what this element alpha does. Okay? And then in the last few minutes, I want to talk about the latter part, the other problem, when we can lift up to isogeny. So this builds on some very deep theorem by Chai, Coran, and Franz Lord. And I'm going to just state precisely what's going on. First, we need a definition. So they introduced this notion of residual reflex condition for a CM field L, so the field generated by a Frobenius element. Actually, this works also when this is not a field, but is a product of fields, but let's not worry too much about this. So the residual reference condition is satisfied for F if we have two parts. So one is that the Shimura-Taniyama formula holds for the CM type. So this Shimura-Taniyama is a set of congruence or p-adic congruences. Basically, it tells you that this complex structure that you can put on a torus of the potential canonical lift is coming from characteristic P. So this is basically the content of the Shimura-Taniyama formula. You have like a bunch of complex structures on this tori, but you want to sort of one that coming from characteristic P if you're working with a lift. And this, if this is satisfied, this is satisfied precisely when you have like this formula. Turns out that there is always a CM type that satisfies the Shimura-Taniyama formula, basically because you are starting from an Abelian variety of a positive characteristic and then looking at the lift, so there must be one. So this is not a very strict condition. The second one is where the juice is. So from the CM type you can construct the reflex field. This is a field generated by the traces of the images. And then you can form a residue field. Let me go to the next slide. So the condition says that the residue, if the residue field is a subfield of FQ, which you started with, then we have the residual reference condition. So next slide. So this is the two conditions I just put in the previous slide. I'm just repeating. So one, Shimura-Taniyama, and two, the reflex field is small enough. And the theorem says that when this is satisfied, we can lift canonically an Abelian variety in the isogeny class. So as I told you, the first one is not really so strong. There is always a CM type that satisfies Shimura-Taniyama. And the second one, the way I think about it is that the residue field of this reflex field acts as more or less the minimal field of definition of the reduction of the lift. So if this field is small enough, it's inside of Q, then we know that we have a canonical lift. So that's the theory behind. And they prove that there exists one, and in fact from the proof you can deduce that the endomorphism ring of this Abelian variety is the biggest one, is the ring of integers of the field, which sort of goes in the opposite direction of what we wanted. We wanted the endomorphism ring to be small as possible, so we also proved this accessory result that tells you that if you have a separable isogeny from an Abelian variety to another one, then also the target of this separable isogeny admits a canonical lifting. So using separable isogenies, you can sort of push the endomorphism ring of what you can lift down in the tree of the endomorphism rings. Okay? And yeah, now I have 2 slides of numbers, which I don't know if you are interested by. I made all this computation, so I said, okay, let's put them on the slides. So the content of this slide is that our machinery almost always works. So it works. In practice, we know that so the residual reference condition is, so here I'm listing the isogeny classes where it's not satisfied, so you can see a bunch of zeros, so it's almost always satisfied. And also Theorem 1 allows us to handle almost all the isogeny classes, or at least a big chunk of them, and Theorem 2 allows us to handle almost on the one that we are missing. So from this table of, this is the number of isogeny classes that you get in dimension 3 for F2, F3, and F5, and F7, and only I'm considering the square free because that was an essential hypothesis. I think we are missing only 13. So from all these isogeny classes, we are struggling. We don't know what to do. Our machinery doesn't work only for 13. Curiosity, they all happen to be defined over F2 and F3. I don't know why this happens, if it is a coincidence or not. And then more numbers for dimension 4. But yeah. Again, here the trend is similar. So we get that our machinery works in the biggest proportion of the cases. Okay. Oh yeah. That's the shame line. So for 9 of them, I mean, the computation of the isomorphism classes is not finished yet. So. And it seems to be too big, but it's okay. I have to put it there for the record. Okay. Yeah, this is everything I wanted to say. Thank you.